morning and welcome back. This will be the hands-on lecture, so please get your laptop prepared. And we'll only have 2 slides, and then we'll just go through a notebook. And so I hope you can just follow our path to run the code one by one. We will not let you to write codes today. We already prepared everything, but I think it's a good practice if you can follow us and run everything. Okay, so I'm Po-Chi Guo. I'm from Taiwan National Tsinghua University. And yeah. Yeah, thanks. Okay, those are my students. Yeah, and also Frank is also from Taiwan. He's now in postdoc in the lab. Yeah, so later Frank will start to introduce some of the environment setting, and then we'll move to my part, and then in the afternoon I'll give back to Frank to talk about some possible pitfalls in our model. Okay, so Frank.
So hello everyone. So it's our honor to have Dr. Po-Chi here for the lecture of the deep learning for Xrays. So we combine the session in the morning and the afternoon together for more flexibility. So first thing, we need to navigate to these 2 links first. Yeah, so now for everyone, please go to the first link to make sure you know your assigned GPU number. It's very important. If you mess it up, you'll kind of crash others' program. So yeah, just making sure you have the GPU numbers.
Just let me know if you have any issues. You can just use a tick, and I'll come to you. And the reason we need your number is we try to assign every of you a single GPU. So if you use the wrong number, maybe you won't be able to have the resources. Okay,
so has everyone got their GPU numbers? Okay, cool. So let's go to the second link. Yeah, the GitHub link.
So do we put a link on Slack?
Not yet.
I think you can also find a link on Slack. You can the repo.
So after you open the page, you'll see this GitHub page. So let me briefly give an overview of this session. So in this session, we are going to do a pneumothorax classification using deep learning. So yeah, just a quick review of what's a pneumothorax. A pneumothorax happens when the air enters the space between the lung and the chest wall. So the air accumulation can compress the lung and causing partial or complete collapse. So treatment includes the air removal using chest tube or needles. So this is how it looks like on a chest X-ray. So you can see that, if I'm not wrong, that it's a very big pneumothorax here. So in this session, we are going to use 3 data sets. We created 3 data sets just for education purpose. So there are data 1, data 2, and data 3. And there will be around 2,000 images for data 1 and data 2, and around 500 for data 3. We are going to use data 1 and data 3 for training the model and use data 3 as an external validation data set. And the deep learning framework we are going to use in this session is Keras. Keras is a high-level neural network API designed for easy prototyping, and so that means you can build the model really easy. And then we are going to use the TensorFlow as its backend. And for more information, you can find the link here to learn more about the Keras. So yeah, let's download the material for this session. So you can also find the code in the storage, the storage that store the material of all the sessions. But here we are going to use Git to clone the repo. So can everyone please now open the terminal? So yeah, let me do it here as well.
Yeah, you can either click the icon of the terminal or you go to the file and.
So you can go to new and then terminal to open a new terminal. So are there any questions about like how to open the terminal? So let's go back to the GitHub page. So after you open the terminal, you can just follow the step 2 to 5 here by simply click the copy button here and then paste it back to the terminal and then hit enter. So after you finish step 2 to 5, you'll see a folder here in your home directory. So it contains the material that we are going to use in this session. So let's double click and go into that folder and you will see a lot of files here. So yeah, so has anyone like So in this folder, you will see many files, including the files end with .ipynb. Those are the notebooks that we are going to use in this session, and they are prefixed by the numbers. And this number indicates the order of execution. So you can, after this session, if you want to review this material, you can just follow the numbers to execute the code. And we also have data1, data2, and data3.csv, and these are the files of the information of the data set. And you will see a folder, result folder. So this folder is going to store your evaluation results of your model. And we also have a folder called supplementary. There are more materials that can be used for your information in the future. Okay, so now let's open the first notebook, which is 1-1 model training.py. So yeah, let me wait a second for everyone to open the first notebook. So,我等他们一下。
再回到刚刚那里，一个 GitHub。看不到那个要选 torch。
So after the notebook is opened, please navigate to the upper right where you can switch the kernel. Make sure you select torch-tf.keras. This is the environment that we are going to use in this session. So, as you can see here, we have multiple environments installed in the instance. So the environment is so basically the environments store all the packages, the Python packages that you are going to use in this project. So for different projects, you will have different environments. So in this session, we already configure an environment for all of you. So it's called torch-tf-keras.
Yeah, if you remember yesterday in Satoshi's lecture, you have to install something, right? But if we already have the environment, that means you don't have to install anything. You already do everything.
So please make sure it says torch-tf-keras on the upper right here. So okay, let's move on. So here comes the very important part. Please put your GPU number in the first cell. And for me, it's 0, so I'm going to put 0 here.
Does everybody know or know how to get their GPU number? They not know their GPU number?
And you may find additional steps after this step. These are not necessary. So yeah, it's how we build the environment for you. So if you want to run this code after the data song, you can follow this step to create the environment. But yeah, it's not necessary now.
Yeah, so if later you want to use your own laptop, your local server to run our code, you have to build an environment because we add the required package in the CXR file, so you have to follow this step to build your own environment. Then you can run our code inside your own.
So if everyone is finished the first step, filling the GPU number, then we can begin. Let me pass to Pochi.
Okay, so for the first part, I'm going to talk about how to build your own CXR model. So just follow the notebook, and I hope you know how to run the cell. You can just press the shift and enter, and you can run it. And if you get stuck, like me, maybe you can try to reload.
But that's just a variable. Huh. Like, not doing anything. Did it run on yours?
I think
that getting this error. I think it's something about the GPU.
Oh.
About NumPy. I think it's something about.
Oh yeah, because the NumPy version. So yeah, so if you have this error, you can follow the steps in GitHub. In our GitHub, we have to use long key. Yeah, so maybe can go to our repo.
The repo itself.
Yes. Yes. And scroll down. So that means we have to follow.
Let me try this.
Yes. So yeah, so if you encounter the problem that's saying your NumPy is something wrong, then you have to follow the steps in our repo. Okay, so that means you have to build your environment. Yeah, but it won't take long, so you can just run those instructions. And the reason is because the version of our NumPy is different from the version they used yesterday in Subclasses session. So if you install the NumPy yesterday, you might encounter this kind of issue. So please build your own environment.
So this is a real-world machine learning problem, right? So your houses and rocks are not the same, right? Your building blocks. So your environment is where you'll build things. And there are best practices for building them. And the way to do it is sort of like the Conda environment. So you can look up something like that, how to best practice and share environments. But this is a good sort of troubleshooting process for this. But, yeah. And we can also show like the requirements and why it's easy. Other people should be able to replicate what you're doing, and including versioning. So it's super important if you're going to work with Python. Maybe that's why people don't work with it.
Yeah, setting up the environment is the most difficult part in our session. Okay, but fortunately, I have a backup. So I have another server to run the code. But please let us know if you won't be able to run the code on. Yeah. Oh, it works now. Okay. Yeah, cool. Okay, so if you get the GPU resource, there will be result showing your GPU number. So that means you already have the GPU to train the model. Okay. Yeah, and there are some warnings, but you can just skip it. Okay, and then you import the packages we need in the following steps. Okay, so you can see we don't need to install any package. Okay, and then I'll start from the model architecture. You can design your own model architecture. And remember, our task is to detect the pneumothorax. Okay, so it's a binary classification task. Okay. Yeah, so first, I will try to explain every hyperparameters, every terms you can see in the code. I'll try my best and use some everyday analog to explain what does this parameter mean. Okay, so first you have to assign the size of your image. Okay, so here you can see the image is 224 by 224. It's a square, and there is number 3. Does anyone know what 3 means? If you
It was hinted at yesterday.
yeah, if you listen to Marley's talk. Yes, channels. And so why there are 3? Yeah, RGB. Okay, but you might be curious. In the trace X-ray, you only have gray level. Why do we need 3 channels? And how to make the one channel gray level to RGB?
I think that's because the model is pre-trained on RGB images, so that we want to to keep the grayscale discrete time so that we coincide with the model.
Yeah, exactly. Okay, so that leads to our second part. That is, we are going to use a pre-trained model. Okay, we are not going to build a model from scratch. We will use the pre-trained model. Okay, so we will use the ResNet here. You can see ResNet is a kind of pre-trained model, and it has been trained by millions of natural images. Okay, so it can do a pretty good job to classify dogs, cats, elephants, something like that. Okay, so we will use the ResNet 50. Okay, and for your information, some of the parameters here, like the weight, means that you will use the weights they pre-train on ImageNet. ImageNet is a huge data set for natural images. Okay, and include tab means that you are not going to classify dog and cat, right? So you have to remove the last layer for classification. Okay, so as I show by this picture, our pre-trained model is a base model, because you can see I put the pre-trained model into the base model. Okay, so this is our base model, which is the ResNet 50. Okay, and here, this is the input shape, 224, 224, and we have 3 channels.
So, and I mean, everyone can see we are co-teaching all day, and so, and there are many, many teachers hiding there. I just want to re-explain this because I know that there are people who've never, ever seen this before, okay? So when you think about that, that's that paragraph, right? That line that is running, just go back up, right? So when you work with deep learning, you have to pick a package that you like. So Pochi and Frank picked Keras, right? So that's a wrapper for a package, and other people use PyTorch. How many people use PyTorch for? Okay, so you can see them. Is there a reason why you pick one over the other? Yes? I can't hear you well. PyTorch can handle what? Okay, so graph learning, he can be handled by PyTorch. What other reason do people pick one library versus another? Those are the sort of the big ones, right, in medical imaging. Okay, so comfort, right? That's actually the biggest reason because you should be able to phone a friend easily. And if you're going to spend all the time online asking for help, you'd rather do what your group does and uses. Any other thing? Okay, if you're going to customize, you can customize it better for PyTorch.
PyTorch, yes.
Why did you choose Keras?
I think Keras or TensorFlow is suitable for beginners. Okay, yeah, because you don't have to worry about too many codes, too many hyperparameters, and you can just simply build your model. Okay, so that's why we choose TensorFlow.
Good. So if you look at the just slightly up, no, yeah, here, don't go. Right. So pretty much the code here is saying from Keras, there is an application. This is a line you can put on GPT, and it's going to tell you what it's doing. This is a common syntax of Python. You're going to import ResNet. So Pochi could pick, when on imports, he could just put a tab and import a different architecture. The reality, one, is that you're going to, as you'll hear me repeatedly say, you're going to read what's been published in what you're doing. So if you're working with chest X-rays, I think DenseNet 121 is really what gives you the state of the art, right? So that's most likely, but here we need to be efficient to go through all the lessons. So we're using a very light architecture, but you can change sort of the architecture you want from that line. And then most of the images, they are loaded as 224. So all the work we did yesterday for pre-processing should be preparing you for this. And then your base model, you're going to use pre-training. You're not going to use from scratch because you don't have all the images that are required. And we feel like the lower layers that are needed are sufficiently learned from cats and dogs. And that's why Pochi is saying, use the weights from ImageNet, and then I don't want to predict cats, dogs, elephants, so don't include that final layer or the top layer, and the input shape will be 224 by 224. So just looking at that code is sufficient for you to start thinking about model training. Okay?
Yeah, thank you, Judy. Yeah, so if you are curious about what kinds of other options, what kind of other pre-trained model you can use, you can just see the spec on Keras website. So you can see you have so many choices, right? And I would like to briefly talk about what's the difference between architectures. Okay, so you can see there are performance. Okay, right here. If you use different base model, you will get the different performance. But this is the performance for 1,000 object recognition task. Okay, like a dog, cat. Okay, and so you can see they have different performance. And the other thing is parameters. Okay, you can see we have different parameters. The VGG has 138 million of parameters. Okay, and also the depth. Okay, depth means how many layers in your neural network. Okay. Yeah. So the question about how to choose your base model, it depends on how many training data you have. From my experience. Okay. So that means if you have more data, then maybe you can choose a model with more parameters, because parameters is the weight, the weight you are going to train. So if you have many parameters, you have more data to train it. Okay. And also you can see if you care about the time to inference a single image, you can check the speed for each model. Okay, so that means if you want to develop a real-time screening model, then maybe you have to choose one more, which is more efficient. Okay, so let's go back to our notebook. Okay, yeah, and here I also did some comments here. That means you can change your pre-trained model. Okay, so if you want to run it, you have to remove the first symbol, and then you can change your base model from ResNet to VGG 16. Okay. Okay. So is everyone still with me?
People understand up to that, at least the people who haven't worked with medical imaging data. So where people stranded? Are people even able to load anything, or they're still loading the library? Loading the library, that's okay. We'll go back to. So I was able to run through my terminal and install all the things, and I don't have the errors. It's really what's on the GitHub is pretty much what needs to be done. It just takes time. What I cannot do right now is find my GPU, although I'm using the one I had yesterday, so I need to go back and figure that out. But as that process is going, right, we just want to re-explain some of these concepts, and so that it just sort of makes sense, because instead of just running through code.
Okay, so let's continue. And once we have the base model, remember our task is to identify pneumothorax. Okay, so it's a binary classification task. Okay, so we have to design our own output. Okay, so the problem with our base model is that currently the output will be something like 7 by 7 by 500. So we have to do the pooling process. Okay, so pooling means that we try to make a 7 by 7 square into a single value. Okay, so if we use the 2D pooling, then it's just like we turn the 7 by 7 into just a single one. Okay, and why do we need to use the pooling? Because we are going to connect it to the dense layer. Okay, and the dense layer will connect to our final output. Okay, and because we are working on the binary classification, so our output is only a single value. If the output is 0, that means it's normal, and if it's 1 means it's pneumothorax. Okay, so only single output. Okay. And let me run the code.
So essentially, again, I'm just repeating what Poche is saying. You're starting off from a model that was trained to predict cats and dogs to end up with pneumothorax with non-pneumothorax, right? You want to learn what the model has learned in the lower layers, but you have to change your final layer to, remember, if you had to predict 1,000 objects, right? I don't know if it would be what your layer 4 would say there, but it wouldn't be finally one number of classes as you see here, right? So one of the skills you have to learn, and today this is a skill that is easy to learn, is how to read code. Right? You have to be able to go through people's code and be able to read it, right? It's easy, it's an easy skill today because AI can help you to do that. But you're moving, you have 2 options here, but you're using one, you're adding your custom layers at the end so that you move from cats and dogs to pneumothorax, non-pneumothorax by using this global average pooling 2D. So if Judy's not explaining it or you want to learn more, this is what you would do. I would put that in ChatGPT and say, explain this to me.
Yes, that's right.
Yes, Wenya?
I think basically output of the base model is like 7 by 7 by 512. But then when I check the shape, it's like 7 by 7 by 4 times 512, which is
Yeah, 2000 something, right? Yeah. I think I picked up the wrong picture. Yeah, but it's just another ResNet with different number of parameters. Yeah. Okay. So next, we can take a look at our model. Okay, you can use the summary function and model dot summary. Then it will show your huge CNN-based model. Okay, so that's why we are not going to build our own model from scratch. Okay, others have already done this for us. Okay, so we don't have to design our own architecture. Okay, so you can see there's a long list. And at the end, as what Wen Yao mentioned, your output will be 2049. Okay, that's a single value. And then you will use a dense layer to create a single output. Okay, and the other thing I would like to mention is the parameters. Okay, here in the third column, you can see the number of parameters for each layer. Okay, so for example, if you take a look at our last layer, you can see the number of parameters is 2049. Why? Why is it the parameters is 2045, 49? Okay, yeah, so the reason is we are going to create a single output, right, from the 2045, 49 values. And so we will connect each element to our output, okay? So the number of parameters equals to the number of lines here, okay? So this is a 2000 vector, so we will have 2000 lines. And those lines are the parameters we are going to train. So you can see the total number of parameters is quite huge. Okay, and the other questions I would like to ask you is about what is non-trainable parameters? Why there are some non-trainable parameters in our model? Yeah, but I didn't freeze anything, right? So why? Yeah. Okay, so what are they? What are they? Yeah, but actually, if you don't have to set up any parameters, they will not show in here. Those are not parameters, right? So we have the non-trainable parameters, means that we have something we can adjust, but we don't have to do that. What are they? Okay, it's a quite not a very frequent asked question. So the answer is inside the batch normalization. Okay, you can see there are some layers with BN, means batch normalization. And normalization is like something mentioned yesterday. You can normalize for certain variables. And here we try to normalize the images within the batch. I will talk about what is batch later. Okay, so normalization means that the model have to learn the average and standard deviation of each image. Okay, so that's also a parameter, but it's not trainable. Okay, it will learn by some statistic analysis. It can calculate the average and standard deviation. You don't have to train it, right? So those are non-trainable parameters.
What are some other non-trainable layers? Types. Nobody knows. So based on this concept, batch normalization, right? You're not training that layer because it's performing a function on the data from the preceding layer. So what else would be a type of non-trainable layer? What do we do to regularize or normalize our models so they don't overfit on data? Dropouts. That's the only one I know. Are there others?
I think that's pretty much so max. Yeah.
Frozen layers.
So what are frozen layers?
Layers that are frozen. Okay, what does that mean? Thank you. So one of the challenges we have in medical imaging is that the medical imaging data sets, no matter how large we make them in our lab, are still really small compared to the general imaging data sets, right? So in this example, we are using ImageNet, or let's say, for example, we're using ImageNet as a pre-trained weight coming in. What that model has done, when you look at the early layers in any deep learning model, it's learning very basic features like contrast between a light and a dark edge, which then progresses to learning a shape, which then progresses to learning what an eye looks like, which then progresses to learning what a dog
example from Jeremy Howell that shows
I'll try to find it for tomorrow. There's this really cool video
Yeah.
from almost a decade ago now that actually inspects the various layers live in a deep learning model and shows you as you go through what features are being detected. So if you had to train the model from scratch using 1,000 or 10,000 Xrays, you wouldn't have enough data to train all of those layers from scratch, right? So what we do is we take the pre-trained weights and use those layers that are already pre-trained from the incoming data and then just tune the back end because we have data scarcity. Now, as data set size grows and computational power grows, there are a lot of groups that are working on actually training radiology foundation models or radiology models from scratch because they have 20 million or 10 million exams or images to work on. In that case, you would not have necessarily frozen. But the example we're giving here, because we've got a couple thousand cases, we freeze certain layers so that that memory of what does a border of something look like. What is the chest wall, has similar features on an X-ray to, this edge, right? A light edge versus a dark edge, just contrast between two groups of pixels, right? And so that's what's in those earlier layers that we're taking advantage of, so the model doesn't have to learn that from scratch.
Yeah, so this is what Harry's explaining. So during the training process, our model will learn some basic feature at the beginning, and then the feature will be become more and more with a meaningful concept. Okay, so if we can freeze some layers, that means we don't have to retrain the model because they are just learning very basic edge or corner. Okay, so we can freeze the maybe the first 10 layers and then train the other layers.
So so this is you're loading images, right? And you are trying to predict an Audi car, right? And you don't tell the model what are the features of an Audi car. It has to figure out, right? And I like to explain this as like going to climb a mountain and then coming back, and you have the truth and what's not, what's incorrect, right? So all these concepts should be starting to, I just want you to make a mental model so that you can go back and either say, okay, I understand this, I'm going to be a data set person, or okay, I usually code in non-imaging data, but I understand the basic components. So now that means this weekend I can do more on imaging data because I'm getting the framework for doing this. Or I will be like Judy and Harry or Pochi, who's supervising students, and I just need to be able to understand what they're doing, right? There's so many directions everyone in this room can do. So if you are trying to predict an Audi car, the earliest lesson, the earliest layers, right, don't matter. It's just predicting. This is random. It's a shape, right? That's what the model is learning, and it's going to keep seeing your data through multiple times. But we want to make sure that the activations being done in your training, the model is not cramming what is the truth, but it's learning something. So to prevent the cramming, then you have things like dropout, where you just fill holes, and these concepts are going to be explained, here. You fill holes as you go along, but the earliest basic layers are just learning shapes. So these are okay for medical imaging. Now, this specificity here for wheels may not be very relevant for medical imaging, right? So then you want to drop those layers because you want for those more advanced layers for it to learn what's the edge of a lung or what's something else, right? But we don't have enough data. So for medical imaging, you always will be sort of this doing fine tuning. You will be picking a model that's been trained on cats and dogs or something else, but that's changing. That's what Harry is saying with the larger foundation models or the embeddings, as you'll see this afternoon, and they will be, you're just coming back to do this final training. So don't get so lost in the weeds, and I just want you to get at least what's the pipeline and this, why is it different from medical imaging? So Pochi, go ahead.
Okay, so once we have our own architecture, and we have to compile the model. And what's the purpose to compile a model? I would say there are three important steps or three important factors you have to set up. The first is the loss function, okay? And then the learning rate, okay? And also the optimizer, okay? And I'll try to explain what are they. So let's start from the loss function, okay? And here we define our own binary cross entropy. And because here we add a special factor that is a label smoothing, okay? And I think this is quite related to what Judy has talked about in the previous session about the labeling, okay? Because right now we get the label which will be either 0 or 1. Okay, 0 means no finding, 1 means pneumothorax. But can we 100% believe the label is correct, maybe not, right? So maybe I just 90% believe the label is correct. So I can try to smooth our label by 0.1. That means all the label 1 will become 0.9, and the 0 will become 0.1. Okay, so that's label smoothing. Okay. So I run this one. And let's talk about the loss function. Okay, so here we define our own loss function, and we put it into the compile function. Okay, we assign our loss is BCE. BCE is what we just defined. Okay, so what's loss function? And I would say loss function is something just like how teachers grade student. You have to have your own strategy, like the first exam times 0.3 plus the second exam times 0.2, something like that. That is your loss function. Okay, so at the end, if the student get 90%, 90 for the scores, and the total is 100, so his loss is 10. Okay, so that's loss function. Okay, so we know when we're trying to define loss function, we have to know the ground truth, the true label, the true answer, okay, and then our prediction. And it's something like we will calculate the difference between the true ground truth and your prediction, but we're trying to use some more advanced function we call the entropy. Okay, and entropy is something we can measure the difference between two distributions. Okay, so for example, here is the equation for binary cross entropy. Okay, so if you take a look at this, this just calculate the log of your prediction times your ground truth. Okay, so for example, if these are the examples you are using to train your model, then maybe the first one is the label is 1 and the second one is 0, and your prediction is 0.8 and 0.2, right? It looks quite good, right? So you can put those two values into your loss function, then you can calculate. And the result will look like this. If the ground truth is 1, okay, that means this is pneumothorax. And then if your prediction is also 1, okay, the x-axis means your prediction. Okay, so your prediction is also 1, then you will get the 0 of the loss. That means you make a perfect prediction. Okay, but what about if your prediction is 0, but your ground truth is 1? You will get a really large loss. Okay, so your model will try to adjust those parameters based on the loss they calculate. Okay, and here I also try to find a figure to visualize the difference, the entropy of two distributions. So if this one is your ground truth, is your answer, and the green one is your prediction. As you adjust your model, as you train your model, your prediction will change, right? So the distribution of the green one will shift. Okay, so what is the best parameters? Okay, you can see if my distribution of prediction close to the ground truth, my cross entropy will decrease. Okay, so that means if I overlap two distribution, I will get the smallest entropy. That is the best model.
Okay, I think you're doing a great job. I'm just explaining for my people who've never ever seen this, so just repetition helps. So if you had a student, like we have students here, you make a mistake, right? The way to track that is the loss function. And you have, yesterday we saw a form of loss function, which is the MSC. Remember the work with Saptashi trying to show us the length of stay, right? You need to know how far you from the truth. So binary cross entropy loss function is also for binary tasks. So your loss function is guided a lot by the task that you want to do. So we've said you don't have all the enough data now. That's changing. You have medical imaging data. You're going to start off from loading a pre-trained model. The only way to know that the best pre-trained model is to read the literature or ask people. So this pipeline is used a lot in our lab, right? Because once you have it, you have it. You know, you may change a few things, but you know, you just are changing a few things, but you're going to use ImageNet. So you're going to preload that data. You're going to then fine tune and say, look, here are the loss functions. But you need to know, is the model learning the right thing? Is your student learning the right thing? If you say, guess the number, they make a wrong guess, you penalize them. So you see that high bar that is jumping off the loss function. When they're very close to the truth, that's what you want to do. So that function that is tracking this this visualization is the BCE, okay? Maybe at least a nod if someone is, okay, good. Okay.
Okay, then we'll go to the optimizer and learning rates. Okay, so optimizer is some kind of algorithm which can lead you to the lowest point in your loss function. Okay, so here let me try to explain the figure here. So you can see the x and y. Those two x's are the parameters you are going to train. Okay, so if you change your parameters, you will get a different loss. Okay, the z is the loss. Okay, so for example, if you choose the first parameters -4 and this is also -4, you will get a loss. Okay, so if you have two parameters, then your loss function will look like a surface. Okay, then the optimizer is you trying to find the lowest point in this surface. Okay, and if you ask me what kind of optimizer I will use, I think 80% of computer scientists will just say Adam. Okay, but I'm not going to talk about Adam. You can just imagine it's a calculation manner to lead you to the lowest point faster. Okay, and what about the learning rates? Learning rates means that if you're trying to go to the lowest point, then your step could be large or small. And so learning rate is if you choose a smaller learning rate, that means every step will be small. Okay. Otherwise, if you choose a larger one, then you will go faster. But what's the benefits of choosing a larger learning rate and smaller one? Any? Yes. Yes, speed. So everyone loves the model to be finished faster, right? So why don't we just choose the very large learning rate? Yes. Yeah, exactly. Okay. Yeah, so I show you a figure here. This is the optimal learning rate. Okay, so you can reach your lowest point. And this one is a little bit slower. Okay, so this is a low learning rate. But if you choose your learning rate too large, then you might miss the lowest point. Okay, then you might be just walk around here and here. Okay, but you never find the lowest point with the smallest loss value. Okay. And so I also leave some notes here. Yeah. Okay. Great. Yeah, but what you can see is we choose a relatively low learning rate here, but feel free to try other learning rate like 0.01, and you'll see the difference of the speed during your training process. Okay, so for compiling the model, you have to assign the loss function and then optimizer learning rate. And the last one is a matrix. Okay, Metrics is something you will use to evaluate your model. You have to supervise the model training process. So you have to come up with some metrics to evaluate. Okay. And here we just use the accuracy. Okay. If you go up, you can see we use the accuracy. Okay. And as a lecture yesterday, we already know what's accuracy. And I would say accuracy might not be the best metrics to evaluate your model. You have to consider other metrics such as AUC, precision, or recall, based on your purpose. Okay. Yeah, so here I leave the comment. You can try to adjust your learning rates and also your metrics. You can replace the accuracy by AUC. Okay, everyone's good?
I'm seeing some notes.
Okay, so now we already have our architecture. We tell our model how to find the minimum point, find the smallest loss, and then we are ready to train the model. Okay. But what's missing? We still don't have data, right? So we are going to talk about our training data. Okay. And the first thing I would like to mention is the batch size and epochs. Okay, those two are very important terms during your training process. So what's batch size? Okay. I think I give a nice explanation here. That is just like you are trying to bake cookies, and there's a limit space of your oven. Okay, so you have to separate your 100 cookies into 555. Okay, so that's just what we are doing here. We try to set out the batch size. That is how many data you are going to use for a single iteration. Okay, so if I have 1,000 training images, and then the batch size, if I set the batch size to 100, which is equal to the total number of my training data, and then it will only take one iteration, okay, to adjust all the parameters, all the weights, okay. And if I choose a batch size to 500, that means I have to adjust, I have to calculate the loss twice, okay. So 500 images will decide the loss and then to adjust the parameters. And then again, the other 500 will train the model again. Okay. So the different number of batch size will lead you to the number of iterations per epoch. Okay, so that leads to our next term, epoch. Epoch, you can just imagine you train a model, you have to train it several times. And each time we call the epoch. Okay, but within a single epoch, we will have several iterations based on your batch size. Okay.
Can you explain that again? Sorry.
Okay, yeah, so we have to train our model many times, okay? And we will use our 1,000 images several times, okay? That's called the epoch. We will train, use all the 1,000 images, train the model, that's the first epoch. And then we'll do it all over again, that's the second epoch. Okay, but how we calculate the loss to change our weights, our parameters, it depends on the batch size. Maybe we will not using all the 1,000 images once. We will separate into two parts. Okay, so 500 images, we will calculate the loss. And this is called the one iteration, not epoch, iteration. Okay, and the second iteration is another 500 images. So after two iterations, we finish a single epoch.
So the batch size is your number of images, right? I guess we could think that you want in the oven, right? You want to bake 1,000. You have your target is 1,000 cookies, so you can split them twice to cook them 2 times, right? Or you can split them 10 times, and you'll have to learn those times 10 times. So the iteration, I believe, is when through all the data, when your model has seen all the training data, and then it moves on to another training cycle. But it's not that your model looks at all your data once and learns the right thing, right? Everything is stored always in the loss function. No, the stochastic gradient descent, but what it's learning, but your model may need to see your data 5 times or 10 times, but we don't know sort of how many times are going to be seen. But because you cannot load all your data at once in your oven, you have to split it into smaller sort of, I would say that's when you bring the epochs, right? So the epochs now are the small samples. In one training cycle, your model is going to see 10 10 subsets of the cookies, so that's going to make one cycle. Is that more confusing or? Yes, morning.
Let me try to help to defend the computer scientist. First of all, my apologies. I have no idea why we pick a very confusing word, epoch, that nobody understands what it means. But a practical consideration is that, for example, we have 1,000 images. Okay, we make it more extreme, right? We're changing like large models. Like maybe we can provide you guys easily 10,000 or 100,000 images. Okay, assuming we have 100,000 images, we check out. However, to fit that 100,000 to the GPU, first of all, it may not be even possible due to the memory issue. And secondly, it may take forever. Okay, so that's not practical. So in practice, rather than swallowing 100,000 images at one go, which we call it epoch, I know it's a very funny word, but nobody knows what that means. You chop it down into small pieces, we call it a batch. Okay, a batch size usually is much smaller. 10, sometimes some images like MRI, which is a 3D image, or 2. The good news is that it allows AI to learn not a lot, but at least very fast, and fits into the GPU and makes it possible to learn. Right, so it allows to, rather than buying 100,000 in one go, it takes a small chip out of it, and you can repeat this exercise many, many times. Okay, until AI, by doing these small bites, until it covers the entire 100,000 with X number of batches, then we say that we finish one epoch of training data. And again, in real life, one epoch is still long. Because we repeat the same exercise many, many times, probably usually 10 to 30 epochs, practice, or even more. Okay, so I hope that. So at what point do we once we every iteration? So every iteration we calculate the loss function, and maybe ask the AI that just based on this small byte, like probably just 10 images, try your best to minimize your loss. Okay, but that won't be perfect because you only see 10. But it's good, right? Better than nothing. So, okay, now I give you a second batch, this is another new test. You optimize yourself again, you keep repeating this until you go through the entire 100K. So now you're a lot better from scratch, but still won't be enough because every time you only see 10 rather than 100K. So that's why we need to run a second. I hope that's.
Thank you.
Yeah. So question: if you have 1,000 images, okay, and your batch size is 100, how many iterations? Epochs? 10. Okay. If you run that model for 10 epochs, how many times will you process your 1,000 images? 10 times. Okay? So every epoch you are number of epochs is the number of times you process your whole data set size. Is that correct? Make sense?
Yes.
Okay.
Yeah, so as Maureen explained, so the consideration, the decision of the batch size depends on what kind of GPU you have. Okay, so if you have a GPU which can fit in more images, then you can choose a larger batch size. Okay, but if your GPU is not really good, maybe you have to change your batch size to 4 or 8 instead. Okay, so that's a decision for batch size. And what about the epochs? How many epochs we need to train the model? 100, 200, 1,000? Yes.
I don't think it matters because you stop it early.
Yeah.
You would do the entire thing.
Yes.
But I just one clarification question. So does batch size and learning rate have a relation?
Batch size and learning rates. Yes, there's relationship, and for me, if I choose the larger batch size, then maybe my learning rate could be larger. Okay, because I will go through all the images. Okay, so I calculate the loss, and then I try to adjust my weights so I can make a larger step because I'm quite sure the direction is correct. Okay, but if I choose a smaller batch size, for example, if I try to calculate a loss for each image, then and maybe I have to smaller my learning rates because every step I'm not sure because I just look at one image. So I will take a step and then the other image to take the other step. And in this case, my step will be smaller. My learning rate will be smaller.
What do you mean by loss? Like what kind of loss?
Oh, the loss. So the loss is like what I just mentioned. You can calculate the difference between your ground truth and your prediction. Okay, so for example, I get a single image. Okay, I will use this image to train our model to adjust the parameters. Okay, so I put my image into my model and I get a prediction like 0.2, but my answer is 1. Okay, so the difference might be something like 0.8. That is my loss. Okay. Yes.
So, yeah, go ahead.
So going back to your question, you asked like how many epochs do you need? So I would imagine that like as you increase epochs, you would have like less, hopefully like less for loss. Like you'll have like a smaller like number.
Yeah.
And so I guess there probably is a point where it would plateau and it doesn't
Yes.
get better. So I think that would depend on like at what point you see that plateau.
That's right. Yeah, that's what we are going to talk about later. Okay, if we don't have any strategy to early stop or to stop our training, and then we have to care about how many epochs we are using. But if we have the early stop strategy, maybe we don't care about how many epochs. Okay, I'll show you later.
He has 2 questions.
Okay, so it's because I'm not sure what.
The question was, I did not understand why we're doing label smoothing.
Okay, yeah. So the reason we do the label smoothing, as I mentioned, I'm not 100% believe the labels are correct because as what Judy mentioned, our label is coming from the NLP algorithm extract from the radiology reports. Okay, so maybe there are some noise for the label. So that's why I will not set our label to 0 or 1. I will try to adjust it to 0.1 to and 0.9.
Yeah, because this is a binary task, right? Something is there or not there, right? So we need 0.5, like, is that there or not there, right? So we need to either say, bring everything close to 0 if it's absent, and bring everything close to 1 if it's present.
Yeah, so number of epochs is exactly having the relationship with the overfitting. Okay, so if you don't have any strategy to already stop during your training process, then you set your epoch to 1,000, you train it 1,000 times, and it will absolutely lead you to overfitting. Okay, because you over relied on your training data. Okay, so that's another very good practice. Yeah, and I also leave some notes here. If you have time, you can go through them. I put the benefits of increasing or decrease the epochs and batch size. Yeah, so you can also try to change the batch size or epochs, and you will see what's happening in your following training process. Okay, so now we are ready to load our data, and we will split our data into training, validation, and test. Okay, and I believe yesterday we heard the reason why we have to do that, but I would like to repeat it again. That is, we can only test our results using test set once. Okay, so I put the figure here, and I try to explain why we need the validation data. Okay, so first let's imagine the blue one is the training curve, and the y-axis is the performance. Here, this is the accuracy. Okay, so if you get higher accuracy, that means your model is better. Okay, so the blue one means the training data. You can see the trend will keep going, right? And the x-axis means the epochs. Okay, so as you train more epochs, your performance for the training data will keep increasing. Okay, and it will reach maybe 99%. And if we take the red one as our testing data, what will happen? If we test our testing data several times, what will happen? What kind of mistakes?
So this is a fundamental question even from yesterday, right? So you have your training and test data. If you keep exposing your test data multiple times, what do you think is going to happen? Yes?
Data leakage. Okay.
Correct, yeah. Right? So memorizes or also data leakage, right? So you'll have leakage between your training and test data set.
So you cannot just choose the best one and to report that result and publish a paper. Yeah, but it's quite, unfortunately, in most of the publication, you won't be able to get the real testing data. So we don't know whether they test several times and report the best one, right?
Sally?
So that's why we have to separate our data set into training, validation, and test. Okay, and during our epochs, during our training training time, we will use our validation data to see how good our model is. Okay, so here the red line should be the validation data. Okay, and so validation data is used to adjust our hyperparameters, like how many epochs and what's the batch size. We can use the validation data to test which one is the best. But after we finish all the settings, we can use the testing data to test the real output, the real performance, just once. Yeah, yes, yeah, training data. And also, but we will not use the validation data for training. We'll just use the validation data to evaluate the performance during our training.
So this concept, I'm just going to explain it again, was from yesterday on these slides, right? You have your data set, you split your training and testing data. Okay, it's also again the language of computer science, which can be very confusing, right? So testing, you put your testing data away, completely away. Then your training data, you can have cross-validation, but most of the time, and this is, I don't want to go down there first, is you have now your training and validation data set. Okay, so training and validation are part of your training data set. So when you climb up the mountain, right, and you're saying, am I learning the right thing or the wrong thing? You still need to know some truth. But that truth, which is what ends up in the loss function, comes from this validation data set, which is a component of your training data set. You're keeping that test data set till you're done, right? But that's, in reality, that's not what happens. When you have a student, they'll use everything, right? And if you keep going, that's what happens with what Pochi is showing. You'll have data leakage in your model. Very, very important concept, okay? So you are using this, and we've said that your model is not going to learn your pathology once, right? It's going to require multiple views of your whole data set, your 100,000 images, and those are called epochs, right? Going up the mountain every time is called an epoch. But there are many, many sort of subset because you're limited by the GPUs that you have. And right, imaging requires big memory. And so you have to then split your data in small batches so that you can load it all the time, but all those will be part of one epoch. When your model has seen everything, is going to be, okay, at one epoch, this is what I learned. And we'll see those curves as they come along. But if you don't understand this, you're going to be in a big problem. Okay. Yes. Correct. Yes. And so now, right, with our students, there's quite, if you're going to do this, you have to set up the infrastructure that is necessary for you to do medical imaging work, right? So when I'm supervising what Frank is doing, then he shows me the loss curves, right? And that's, I don't want to take away from the next session. So there's a way to communicate these results that makes, okay, this makes sense or this is not making sense, beyond just like the AUC of 0.99, right? And you have this, you have running so many experiments. So what our students do, they have this weights and biases framework, and they log all the experiments in there so that if we want to go back 2 days ago to see what was there, it's easy to see, to pull up these loss curves and everything else. Are you all lost or you're learning something? Your loss function? Good one, Musa. Okay.
Yeah, so that's also the reason why more and more journals are asking you to publish your data set or to open your codes, because others can evaluate, to test your code, your data, to replicate your results.
Okay, so oops.
Okay, so after I load the data, you can see I have 1,300 for the training data, and about 450 for our first test data set. Okay. So everything is ready, and here is the reason why we need the validation data, and we just talk about that. And I can show the batch of training data here. And remember, our batch size is 16, right? So one batch contains 16 single images. Okay, so I just show a single batch of all the images, and along with their label. Okay, remember the 0 and 1 means the no finding and pneumothorax. Okay, then we will normalize our images value of pixels into 0, between 0 and 1. And why we need to do that? The original value might be the 0 till 155, and we will normalize it into 0, between 0 and 1. Why? Guess this? Yeah, that's one reason. And I think the easy way to think about this question is our output is also 0 and 1, right? It's a positive or negative. So during our training, we will not let our model to learn a very huge, very small weights because our values are large, are 200 something. Okay, so we will make our output, our input close to our output, 0 and 1. So that's why we try to adjust, to try to make our pixel values between 0 and 1. And that will also make our training to become more efficient. So summarize. Yes, so we are ready to train the model, okay? But I comment those code because we still miss something, okay? Yeah, so if we want to train the model, we can use the function fit, and we have the training data. We already know how many epochs we are going to train, and also we have our validation data. Okay, so of course you can run this code and you can start the training. Yeah, but the question is why we set our epoch to 200. Okay, so we have to keep track of our training process. That's how we can make an early stop. Okay, so to keep a track of your training process, you have to save every checkpoint. Checkpoints means the model after a single epoch, you will get a checkpoint, and then the second epoch, you will get the second checkpoints. Okay, so that's the way we can track our training process. So we will use the model checkpoint and to have some parameters like where we are going to save our checkpoints and how we monitor our model. Okay, so here I will just use the loss function. Okay, so you can see later I will draw the picture and the loss function will be the y-axis to monitor our performance. And I also set the save best only to true. That means I'm not going to save every model for every epoch. I would just save the best one. Okay? So how can we decide the best one? Yeah? And what kind of data we are going to use to test, to get the evaluation of the best model? Validation, right, yes. Yeah, and this is an early step. That's what we just talked about. We don't want our model to train until entire 200 epochs. We might stop earlier because we think the model has been well trained, so we stop, okay? And there are also some parameters we have to give for the early stop, and also the monitor. And the delta means if the loss is, the changes are larger than 0.001, that means our model is still learning something. But if the changes are below 0.001, then we think that it's almost saturated to a certain status, okay? And the patient means that we will wait 20 epochs. if all those 20 epochs have the loss lower than 0.001, then we will stop. Okay, so we will wait 20 times. If the changes of the loss is smaller than the threshold here, then we will stop. Okay, stop our training. Okay, so that means we won't be able to go through entire 200 epochs. We will stop earlier. Depends on the changes of the loss. Okay, the early stop. And yeah, and the other concept is a reduced learning rates, and I just want to use a figure to show the concept. So the learning rate, if you remember, means the steps you are going to for the next step, right? So if you use the static learning rates, that will be something like the pictures on the right-hand side. So every step is with the same length, okay? But if you can have some algorithm strategy to reduce your learning rate, it will like something here. You can start with the larger learning rates. And then if you realize you are close to the lower point, then you can start to smaller your learning rates. Okay, so if you compare those two figures, you can see I only need 3 steps to get to the lowest point. But if I use the static learning rate, I need 4 steps. Okay, so that's an important thing for the reducing learning rate. Yeah. Okay. So how to reduce our learning rate? Yeah, I put some notes here, and there are also some parameters you have to set, and it's quite similar to the early stop. You have to monitor your performance by validation data, and if you see the changes are quite stable, okay, and then maybe you can start to smaller your learning rate. Okay.
Does it follow any sense of chronology? Which one comes before the other? Because I'm thinking you like to reduce the learning rates before you even initiate.
Yeah. Yes. Yeah. So usually you can just imagine if you keep reducing your learning rate, and finally the learning rate will become 0, and that is what early stop is doing.
I was thinking that maybe if you start with that one and then initiate the early stop function, and I'm also not sure how that plays out because from the chronology of the coding, we have the early stop function followed by the reducing learning rate function. And I was thinking that maybe what happens if we stop?
Yeah, that's a good suggestion. Okay, so now I think we got everything we need, and this is just a function, a class we define to plot our training curve. Okay, so maybe you don't have to care about worry about this, and then we can start to train. Oh, checkpoint is not fine. I forget to run. Yeah, if you get a message like me, that means you may miss some of the previous sections. Okay. Yeah, and ideally it might take about 5 to 10 minutes if you have used your GPU properly.
It's a good point for any questions, clarifications. Yes.
So one thing to notice is that we have split the data for you before the data zone. So it's important to know that in the future, if you want to do your own project, you have to split the data into training, validation, and test before you run the model. So in this session, we already did that for you. And we also pre-process all the image using the LUT CEO mentioned about yesterday, and also we pad the image to make them all with the same size. So yeah, that's something we need to pay attention to in the future.
As you look at the training, this is also another time to re-emphasize some of the concepts, right? So you see that we are looking at epoch 1 of 200, right? We've said that our model needs to see all our data 200 times, correct? And within the epoch, we're seeing several iterations, right? There are 85, and maybe what you can see, that you can see the accuracy of the model, you can see the loss, and then you can see the validation accuracy and validation loss, and what's happening with every run, which has different batch sizes, right? So if you don't understand the original concepts, then you cannot see what's happening in the training your model phase.
Yeah, so why we get the 85, the number of 85?
What's 85 in our parameters?
Yes, so how we come up with the number 85? Yes, yes. That's right. Yeah, so if you go back to see how many training data we have 1,300 something, and our batch size is 16, right? So 1,300 divided by 16, that would be around 85. Yeah, so here you can see we already run 8 epochs. So the x-axis is the number of epochs. And you can see the blue one means our training loss, okay? And usually, normally, the training curve, the loss will keep decreasing, okay? But the orange one is the validation loss, okay? So you can see it will come up and down, come up and down. So later, we will use our validation data to pick up the best model, okay? And then test on our real testing set.
Any questions as the model trains concerns? Yes.
Yeah, we'll talk about the distribution in the afternoon session. But right now, I can tell you the number for 0 and 1 is quite balanced. Okay, yeah. And if you have maybe if you have an imbalanced data set, like you only have 200 for the label 1 image, and then you can consider the method they talked about yesterday. You can try to do the augmentation to increase the training data.
And one of the imbalanced data sets will be breast. So we're moving sequential. Number one, we started with tabular data, right, to introduce these concepts, right? Then we transitioned to a little bit of context to process medical imaging data. Then today, we went to ground truths, right? What are your considerations? And then now we're trying to show you what does it take to build a deep learning model on medical imaging. So if you had retinal scans, right? So if in the logistics email, I said you should sign up for PhysioNet because there are many data sets there, right? So if you had retinal scans and you process them well, all you could do is just put them in this pipeline and it was going. Now you should probably give the right label, not just pneumothorax, no pneumothorax, and it does the same, right? But and this you have to say, you never have enough images. I know, sorry for repetition, but you never have enough images in medical imaging. So you'll always require some form of pre-training. And that means you have to load the model, ResNet or whatever model you want. the best way to figure out what that model is to look at the literature. And for chest X-ray, tends to be DenseNet 121. So you load that model, but you have to now provide your 1,000 chest X-rays or 1,000 mammograms to the model for it to learn the fine things that are about medical imaging. And to do that, you have to decide how many times is your data going to see, how many times is your model going to see the data? That's the number of epochs, right? But you cannot load all the possible data sets that exist. You cannot make all the cookies at the same time. So you have to load the data in batches. Several batches make one epoch, right? And you will have to specify your hyperparameters, including your learning rate, because if you take very big steps, you're not going to learn everything. But if you take very small steps, it's going to take you forever, and to be able to get to the end. So the way we decide the steps, right, are the earliest. It's also looking at the result and saying, this is easy for me. I can take bigger steps and take more, to be able to get to the bottom of the valley. But you're tracking this using your stochastic gradient descent, but everything else is the loss that is saying, am I learning something or am I not learning something? Okay, so you have to identify those parameters. I know it's a very simplified way, but this way you can be able to read a paper and re-implement. For the computer scientists, that's the bar. You should be able to read a paper and re-implement the code just by reading the sections, okay?
Yeah, and while we are training our model, maybe we can move to our next session and next notebook, okay, which is 1.2 model evaluation, okay. And so here you still have to assign your GPU number as what you did in the previous notebook.
You are not able to evaluate the model now because the GPU is occupied by the.
Oh, I see. Okay, so if I use number 2, that might work. Yes, yes. Yeah. Okay, so I just go through the first lesson I learned when I become the teacher is don't let your student be hungry. So, yeah, so I will just go through it and try to finish it for lunch. Okay, so let's just assume we already trained our model and we pick up the best one and save it in the folder. So, and then we can evaluate the performance, the real performance, by using our testing data sets. Okay, so here the first step is to import libraries, okay, just as what we did in the previous one. And we will load our best model. Okay, so you can see in the previous notebook, we save our best model here, right? So this is the same path. We'll use this one as our best model. Okay, so once we save it, when we're trying to evaluate the model, we just load it. Okay, load the weights. Okay. Maybe okay, yeah. So because I have trained it before, so I already have the best model. Okay, and after your training, you will also have the model in your folder. Okay, so we are extracting our testing data, and it's just a similar approach. We will normalize the images by 255 to make it between 1 and 0, and we separate our data into positive paths and negative paths. Yeah, but you don't have to worry about that. After you run the code, you will get the testing data. And you can plot some of the testing data here. Okay, and also with the label. Okay. And next, you can start to make prediction. Use your own model. Okay. And the output of the model will be a probability. That means if you get the result larger than 0.5, then suppose this will be a pneumothorax. Okay, and lower 0.5, that would be a no finding. Okay, but of course you can adjust your threshold to 0.6 or 0.4. Okay, depends on your purpose. Again. Yeah, so we can put our testing data into our model by using the function predict, and we will get the output as the probability. Okay, so our prediction will be the number between 0 and 1. And because this is a binary classification task, so eventually we have to make it to either 0 or 1. So that's what I just mentioned. You can decide your own threshold. Okay, and here I just put the 0.5. Okay, and yeah, so you can see here is our prediction for all the 450 images. And so you can see the probability is on the right column. And our prediction will transfer the probability into 0 or 1. And the label means the ground truth. Okay, so I have the ground truth, I have a prediction. Then I can use some metrics to evaluate the performance of our model. Okay. And we can show some of the results.
So in this case, you have to remember what 1 is. So 1 is pneumothorax, and so you can see where the label and the class is correct, right? So this is what you'd show your domain experts so that they can look at the quality of predictions, right? And you want to focus a little bit on where there's discordance, where's the discordance within the false positives or the false negatives, right? Because those give you a sense. You may open this and then you're like, oh, it's because of pre-processing or something else. That's why that's not working.
Okay, and then you can use the matrix. You can show the confusion matrix for your prediction. Okay, and so I would say this one will not be a very good model because you can see there are hundreds of images on this corner, and the perfect model should be just at this end. So yeah, so you can test your model later, but I think this one is not the right one. Okay, yeah, but in addition to accuracy, yeah, just show you can